It's tempting to think that securing a building is as simple as buying a camera and screwing it to a wall. But we've all seen the news footage where a crime actually happens, and the resulting evidence is nothing more than a pixelated, dark silhouette shuffling across a screen. Having a piece of hardware prominently watching the street might deter a casual trespasser, but an intimidating piece of plastic doesn't guarantee you'll capture any usable details when it actually counts. The lens is merely the entry point. Every time light enters that camera, it has to survive a brutal technical pipeline filled with environmental hazards, network bottlenecks, and aggressive data compression. To construct a system that produces legally actionable evidence in court, we have to track the exact journey of an image, step by step, from the physical world all the way to the hard drive. Before a photon ever touches a sensor, we have to engineer the physical space it travels through. Security experts measure ambient light in lux, and 3 lux is widely considered the absolute bare minimum to see anything at all. A modern office might hit perfect light levels during the working day, but after hours, cameras struggle to detect color and detail. To compensate, the environment requires either artificial floodlights or cameras equipped with special infrared filters that sends heat instead of visible light. To capture clear images, lighting must be remarkably even, ideally no more than a 3-to-1 ratio. When bright windows and deeply shadowed hallways coexist, that ratio breaks down. Extreme contrast overwhelms the sensor, turning your subject into an unidentifiable silhouette. You cannot fix this with software later. If poor lighting design destroys the physical details in the room, the camera sensor has nothing left to capture. Once the light is balanced, the hardware must actually see it. Seasonal blind spots, like heavy summer leaf growth, easily block poorly placed lenses. If the primary goal is identifying a suspect, mounting a camera flat against the ceiling only gives you a great view of a baseball cap's brim. To get a usable face, the lens needs to be mounted down at head height. Image resolution is historically measured in television lines, or TVLs. A 300-line grid captures broad shapes, while a denser 700-line grid captures the fine details needed to read a name tag or license plate. Ultimately, the sensor must successfully deliver 4 elements to be useful: absolute optical clarity, enough detail for object identification, natural color representation, and 0 visual distortions. By combining strategic head height placement with a high TVL resolution, the hardware captures a clean, accurate slice of physical reality and successfully translates it into digital data. Now, that clean image has to travel from the camera to the recording room without degrading. Many wireless setups use the open 2.4 GHz frequency band. The problem is, they have to share that exact same airspace with cordless phones, wireless doorbells, and even the radiation from a running household microwave, which causes severe interference. The alternative is a wired IP, or Internet Protocol network. This physical cable routes the data securely, preventing third-party viewing while also allowing operators to control camera movement remotely. But routing a massive volume of heavy video traffic onto a building's existing local area network often causes intense congestion, leading to sluggish reaction times and dropped data packets. Your network pathway dictates if a critical frame of evidence survives the trip or breaks apart into unreadable static before reaching the recorder. The final stop in the pipeline is the digital video recorder. Here, continuous high-resolution video streams bombard the system's hard drives 24 hours a day. 4 variables dictate how fast that storage fills up: the overall size of each image, the frames captured per second, the total number of active cameras, and the system's operational hours. When managers demand 30 days of recorded footage instead of 10, the recorder is forced to aggressively compress the video files to squeeze all that extra data onto the exact same drives. This chart visualizes an unavoidable truth in system design. Any configuration that maximizes storage days directly degrades pixel quality. You cannot increase one side of the scale without emptying the other. If you miscalculate the storage capacity, the system will invisibly crush the sharpness and color out of your footage, destroying its value as evidence right as it writes it to the disk. When you trace the pipeline backwards, you realize how delicate the entire process is. Light reflects off a subject. It enters a specialized lens, converts into digital data packets, and races down hundreds of feet of copper wire. That data only survives if the physical space maintains a 3-to-1 light contrast. The camera sits squarely at head height, the IP network remains uncongested, and the hard drives have the capacity to store uncompressed files. Only when every link in that chain is engineered correctly does an operator sitting at a control desk finally see a crisp, perfectly lit image that holds up under cross-examination. Buying a piece of hardware and bolting it to the wall is an illusion of safety. True security requires the precise alignment of physical space, digital networking, and data storage.